Hi, everybody. What happened to my class? Everybody's gone. You just didn't feel like coming in.
Too close to spring break.
Too close to spring break? It's like 10 days still. That is so close?
Yeah, especially because it's like we were supposed to go to the lessons.
Where's like all these like normally very studious and like with it kids that have just been like just peacing out? Like where's like Amanda and Regina and Emily?
They were lunch. I don't know where they are. They were just here.
How about Jay?
Quarantine, probably.
Oh, yep,
Somebody
he is
on
on the
football team
list.
got COVID.
Oh,
A lot of people.
I see. That is 7 down for the 25 or whatever we have. That's not great. All right, folks, how are we doing?
I'm tired.
You and me both, sister. Well, let's take some time here at the start of class, and we'll take some questions from the homeworks. So, does anybody have anything from homeworks 1 or 2 that they want to ask about? Josh? Yeah, no problem.
Forgot number 11.
On 1 or 2?
Actually, I meant on number 10.
On
number 2.
On homework 2? Yeah, there were some bad mama jammas on homework 2 here at the end that were quite tricky. So what I would do with this one is I would start by doing a prime factorization of 12 and 8. So 12 is 2 squared times 3. And 8 is 2 to the third. And then I can use my exponent of a product property to take these two and kind of combine them together because they both have the same exponent on the outside of those parentheses. Cool there. And then I can do my exponent of an exponent property, and 3/5 times 5 is just 3. And then I can do my exponent of a product property again. So that's going to be 2 to the 15th times 3. And then whatever, if you didn't want to multiply that out on your calculator, that was fine. That's a big stinking number.
Where did it go? 2 to the 5th.
When I combine those two parentheses together, 2 to the third and 2 to the 2nd is 2 to the 5th. And again, I'm only able to combine those sets of parentheses together like that because they have the same exponent on the outside. And there's different orders you could have gone and done that and still ended up at the same place, just FYI, Josh. Macaroni. You could. You trailed off at the end.
So would it still be right if I multiply 12 times 8 and got 96? And then multiply that by 5 and
So 96 to the third is that. 2 to the 15 times 3 to the third is that. Oh, you guys can't see it? So it's the same thing, right? Same number, that's fine. NBD. Yeah. Is that, everybody's happy there though? With Mackenzie's question? Certainly you could have done what you described. That's cool too. So I'm going to start by doing a prime factorization. So 144, what is that? That's 12 squared. So that's going to be 2 squared times 3 squared. So 2 to the 4th times 3 squared. And I'll make that to the 1/3. And then 384, what is that? That's 4 times, no, that's 2 and 162, and that's 2 and 8, so that's 2 and 81, so it's 2 squared times 3 to the 4th, I think. Did you do the prime factorization, Mackenzie? No, I mean, eventually we're going to get rid of those square roots, but I did the prime factorization, right? That's what I'm really asking. I just want to double check because I did it in my head and I didn't want to, if you goof that up, like say goodbye to your chances of getting the right answer, you know what I mean? Okay, so now I'm going to do my exponent of a product. So that's 2 to the 4/3, 3 to the 2/3, 2 to the 2/5, 3 to the 4/5. And then I can combine those 2's together by adding their fractions. To add those fractions, I need a common denominator. That's going to be 20/15 and 6/15 to make 2 to the 26/15. And then similarly, I'm going to combine those 3's together. So again, common denominator, that's 10/15 and 12/15 to make 22/15. So far, so good. Okay. So 26 over 15 is 1 and 11/15. And 22/15 is like 1 and 7/15. So that can be a 2 to the 1st times 3 to the 1st times like the 15th root of 2 to the 11th times 3 to the 7th. So again, what I'm getting here is 2 to the 1st, and then 2 to the 11th and the 15th root, my 3 to the 1st, and then my 3 to the 7th and the 15th root. And if you wanted to multiply those together and get some crazy monster number, you could do that. I would not. Is that okay, Mackenzie? Okay. Maddie, what's up? Sure. Again, if we don't like what we're doing, or you want to ask it like, I did this, is this okay? Or any of those sorts of things, I'm happy to, or like I started doing this and then I kind of got lost. Was what I was doing okay? Can you help me kind of finish it out? Or any of those sorts of things, I'm happy to address while we're doing this, just FYI. These problems, there's usually lots and lots of different kind of fast ways to the finish. So again, if you want to ask about something, that's perfectly fine. Mackenzie?
Is it possible to combine the fraction and put it, I don't know how to start this. What I did is I found the fractions and then turned that into square root, and then
So when you said found the fractions, I'm not sure what you're saying.
the part with the arrows that you had, and then what it equals like that part,
Mm-hmm.
and then I put it under the radical.
So you had like somehow got to like here.
Yeah.
Okay, that's fine, but you still would need to take out a factor of 2 and a factor of 3. And then you'd be left with this. But that's fine. You can think about it that way. That's not wrong. Is that okay? Okay. Maddie, you wanted to see 15, you said?
Yes.
Okay. And this one is just like power right there, folks. All right. 12 is 2 squared times 3. 24 is 2 to the third times 3. And I'm going to put these as exponentials. So far, so good, Mackenzie? I'm sorry, Maddie. You're right. 48 is 2 to the fourth times 3. And then 96 is 2 to the fifth times 3. You cool so far? So I did was prime factorizations and turn the radicals into exponentials. So now I'll do my exponent of a product. So I have just 2 to the first times 3 to 1/2 times 2 to the first times 3 to the 1/3 over 2 to the first times 3 to the 1/4 and 2 to the first times 3 to the 1/5. So the 2's can just reduce out of there. So if I multiply the numerators together, I'm going to have 3 to the 1/2 plus 1/3. And the denominators, I'm going to have 3 to the 1/4 plus 1/5. And if I divide them, I'm going to have 3 to the 1/2 plus 1/3 minus 1/4 minus 1. And now I'm just going to make a common denominator. So I think the common denominator there would be 60. So I'm going to have 30 over 60 plus 20 over 60 minus 15 over 60 minus 12 over 60. Well, because they were in the denominator, right? So let's see, that's going to be 35 minus 12, so 22 over 60. And that can reduce down to 11 over 30. And so I would call this the 30th root of 3 to the 11th. And again, if you want to type 3 to 11 in your calculator and have it spit out a number for you, that's cool. Or you can just leave it as the exponential. I'm okay with that too.
Okay. So is it either one of those with that? So you could either do the exponential way or the way with...
Well, typically the convention is you'd leave it in whatever form you started with, but if you wanted to write that 3 to the 11th as 177,147, you're free to do that. But usually, like, if the problem, oh boy, where did my stuff go? Radicals, usually you write your final answer with a radical. If your problem started with exponentials, you could write your answer with exponentials. But that's kind of just the convention. I wouldn't probably mark you down for that unless the directions say specifically to like write your answer in the same form as the question or whatever. But is that, you're cool? And that one looked pretty nasty, but it turned out to be not so bad because all those 2's just kind of reduced out of their radicals and simplified down. It wasn't so bad, right?
Number 1, maybe 14.
14 from homework 1. sure. Okay, so 324, I think we reduced previously. Or at least I should say the prime factorization previously. So that was 2 squared times 3 to the 4th. And then 768. I think that is something else. Is that 3 to the 6th or something? No, that's 729. Let's see. Four, 5, 6, 7, 8. Oh. 2 to the 8th times 3.
So you can only use the exponent that was given to the next group. Like the 4 that you can only do it to the next group.
So I haven't done anything other than written the prime factorizations.
Okay.
So I haven't done anything like that. So in the first radical, I have a 3 to the 4th, right? So I can pull that out. And I'm just going to rewrite the 2 squared as a 4. And in the other piece, I have a 2 to the 8th, which is really 2 to the 4ths, right? So I can take 2 out twice. I'm left with a 4th root of 3. So when it's all said and done, I don't have like radicals at the end, so like that's as much as we can do. We can't actually subtract them because the radical parts are different. One is a 4th root of 4, the other is a 4th root of 3.
Okay.
Which I think happens more than once in this homework set, right? Those of you that did the whole thing, did that happen more than just that one time? I think I'd had it happen a couple of times. Yeah, I think there's a couple where you didn't actually you simplified them down and not everything was the same, so you couldn't actually add them together, which is fine. Like I wanted to have that happen. Although it feels like, oh, you just screwed that up. It's like, no, I wanted to have a couple where you just nothing to do because there's not always something to do. You know? How are you guys doing here? Mackenzie?
So for number 3 and
Uh-huh.
since it's a negative, would you just put it?
Let me look real quick. This one?
Yeah.
Okay. So 1 over 13 to the 3/7. But we don't like to leave a rational exponent in the denominator, just like we wouldn't want to leave a radical in the denominator. So the next whole number after 3/7 is 1, right? Or 7/7. Everybody agree with that? So how many more do we need to get to get to 7/7? I need 4/7. Everybody okay with that? So I would write this as that. Mackenzie, alternatively, the other thing you could have done is instead of using that property for 1 over, is you could have just started by multiplying the top and bottom by 13 to the 1st, and that'll get you the same thing. So either way is okay, though. Is that you cool? This is like an aside. Edmund?
We do number 6.
6? Sure. So the property I'm going to use one. So that means I'm going to have 10 to the 7/10. That's all we can do. Means 10 is just 2 times 5, so there's no like reducing that can happen there. So that's it.
You also do 1%.
Sure. Ways you could do this. One, you could notice that because the exponent parts are identical, we can use the power of a product property to multiply the bases together and keep the exponent the same. And then if we do a prime factorization of 81, that's 3 to the 4th. And exponent you multiply and you're left with just 3. Yeah, no problem. Oh my goodness. And this is just, this is the same thing I have up there. What did I do here? I don't know, I'm making a big mess out of something here, guys. Hold on one second. Okay. So I'm going to rename this with today's date. It has all our notes on it for today. I'm going to get rid of this page that we've already dealt with, right? Yeah, that's already over there. Okay, drag that back over here. I'm going to copy it. That's some BS. You don't need any of this time in OneNote. I just made a boo-boo here. What did I just do? Oh, okay, there we go. I'll move that back here. We're going to call this Chapter 6, Worksheet 2 again, and then get rid of all of my marks. Nope. Okay. Sorry about that, guys. I realized that and not the blank ones on the notes for today. So I'm just rearranging some stuff here real quick. So that these are still blank if people needed to go back and get them without my work on it. There we go. That's better. Okay. So how you guys feeling about this stuff? Is it going okay? Well, that's good. That's good. What do you want to do today? Do you want to talk about solving stuff or graphing?
Solving.
Solving? Okay.
Which one's easier?
Oh, the graphing's way easier.
Yeah.
But
Graphing.
Graphing.
You already picked solving, though.
I'm changing my mind.
Okay. Okay. So we're going to look at two situations. The first one is a square root function. So let's say our general form for our square root function is going to be this. Y equals a times the square root of x minus h plus k. And our goal here, when we're graphing this, is going to be to select our x's so that y is a rational number. So basically what I don't want is to just get like screwball decimals all over the place. And if we're not careful, that's exactly what's going to happen. So in order to get this, what we need is perfect squares under the radical. So what's an example of a perfect square?
36.
36 is an example of a perfect square. Great. Are there infinitely many perfect squares? Sure, right? Because you can just keep picking another number and squaring it, right? Is there a biggest perfect square? Is there a smallest? Yes. What is the smallest perfect square?
4.
Nope.
1.
Nope. 0 is the smallest perfect square, because 0 squared is 0, right? So after 0, the next smallest perfect square is 1, and then 4. After that is what comes after 4? 9, thank you. And after 9 is 16. So those are going to be the perfect squares that I'm going to use, or at least modify every time when I'm graphing. So this is our first 5 perfect squares. So let's take a look at an example. Let's say we're going to graph -3 times the square root of x plus 2 minus 3. Let's pick a different number. We'll pick 1. All right. So we'll make ourselves a little XY table. I have 5 points in my XY table every time. Where my goal value, the value that I want underneath the radical, is going to be the perfect squares. So look at what I have under the radical. What value of x do I need to choose to get 0 under the radical? -2. Right? Because -2 plus 2 will give me 0 underneath the radical. How about to get 1? -1. Okay. Everybody's good there? How about to get 4? just going to pick 2. And to get 9, I should pick 7. And to get 16, I should pick 14. Is everybody okay there on how we found those x's? Pretty easy to do that in our head, right? Or not difficult anyways to do in our head. Now to get our y values, what do? We just plug the x in and evaluate. The nice part though is that we're guaranteed to get nice, neat numbers because we'll always be taking the square root of a perfect square. So really what I have here when I plug -2 in is I just have 3 times the square root of 0 minus 1, which is just -1. When I plug -1 in, I just get really -3 times 1, or square root 1 minus 1. It's -4. And when I plug in, +2, I get -7. Everybody's okay still? See what we're doing? See where all the numbers are coming from? If you don't, speak up. I'm happy to explain some more or clarify or whatever the need might be. But if you guys stay silent, I assume nobody has a big problem with what I'm doing. In the next step, we'll really generalize this out nicely and formalize things a little bit more. But I figure just like an ad hoc first walkthrough and kind of what we're trying to accomplish would be nice. So that's -13. Okay. So then we'll just plot this stuff out. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So -2, -1, -1, -4, 2, -7, 7, -10, and then 14, -13. Everybody okay with the points plotted? Now, when we draw our arrow, we have to be kind of careful here. Normally, when we draw our graph, we draw it with arrows at both ends, right? Should I do that in this case? Definitely not. Why not? Well, what would happen if I plugged in an x that was less than -3? Yes, exactly. If I plugged in an x that was less than -2, the part underneath the radical would be negative, and we'd be getting a non-real result. So really, my arrow should only be going in one direction. It should only be going, in this case, to the right. Will I be picky about that? Oh, you better believe it. Would I even be picky if you did something like that and had a little bit of tail past the end? Oh, you better believe it. You better not have anything on the wrong side of your first point on your table there. Everybody's okay with that, though? We get where I'm coming from? Okay. So let's make a couple of observations here. So let's kind of generalize this. So when we found our x's in our xy table, what did we really do here? We took our perfect square, and then we just added our value of h to it, right? And in fact, I'm going to write them this way so it's even more clear why we're choosing these numbers. Everybody's okay with me writing it? 0 is 0 squared, and 1 is 1 squared, and 4 is 2 squared, etc. Just to really hammer home the fact that these are perfect squares that we're using. Is that okay? When we found their corresponding y coordinates, come on in, ladies. We were all wondering where you guys were. The consensus were you were all at lunch, so thank you very much. When we found our y coordinate, let's look at what happened. We took our perfect square, or the square root of our perfect square, we multiplied it by -3, and we subtracted by -1. And we kind of did that every time, right? What is -3? That was the coefficient. What was the -1? That was this constant at the end. So what we really have here is a times 0 plus k, and then a times 1 plus k, a times 2 plus k, a times 3 plus k, and a times 4 plus k. Now, you don't have to do it this way. I'm just kind of like shortcutting through some of the stuff. It's not really much more work to plug in your x's once you found your x's appropriately. But, worth pointing out that this first point will always simplify down to just hk. Since you're 0 plus h and then a times 0 plus k, it'll always simplify down to hk. But that's fine. I figure if I write just hk there, the pattern's not quite as obvious. You know what I mean? At least the first time seeing it. It's obvious after I pointed out what's going on, but this is probably the better way to start it. You know what I mean, guys? That's the pejorative guys, not the gender-specific guys. You know what I mean, use? That seems weird, though, to say, doesn't it? All right. So far, so good? We still should talk about domain and range here, though. So the domain is going to look like one of two things, right? It's going to either start at our h comma k point and continue to the right forever, or it's going to start from the left and stop at that h comma k point. Everybody agree with that? So it'll be one of those two situations. And that's how we can tell. So if we're doing x minus h, it starts at h and goes forever. If it's h minus x, it started at negative infinity and stops at h. The range is about the y's. So again, it's either going to start at negative infinity and go up to that point hk, or start at that point hk and go up to positive infinity. Everybody agree with that? And it's easy to tell which one is which. You just have to look at that a coefficient and whether it's positive or negative. If it's positive, you're starting at k and going up. If it was negative, you start at negative infinity, go up to k and stop. So if we went back and looked at our example that we started with, our domain here was h to positive infinity, and our range was negative infinity up to k. Here because the a was negative, and here because we had x minus h. That's basically all there is to graphing square root functions. So not too bad, right? You basically will pick your x's the exact same way, and then you can find your y's either with the little formulas that I gave you, or you can just plug them back into the function. Either is fine. The goal, though, is that you should be getting should be having no square roots left in your y values. Your y value should be a rational number, preferably an integer, but if the a coefficient was a fraction, then you're going to get fractions there. Mackenzie. Yeah, I was going to scroll down here. Yeah, of course. So now we're going to talk about graphing cube root functions. So when I talk about a cube root function, I'm talking about something that looks like this. Once again, the goal is to pick x's so that the y's are rational numbers. So I don't want any cube roots in my y values. Everybody's okay there? So how do I do that? This time we want perfect cubes under the radical. Everybody's okay with that idea? Okay. How many perfect cubes are there? Infinitely many. Okay. Well, is there a smallest perfect cube?
Yeah.
Are you sure?
No.
So what's the cube root of -1? Well, remember that negative 1 to the third is still negative 1, right? So the cube root of negative 1 is also negative 1. So is there a smallest cube root? No, because you can still cube root negatives, right? Is there a biggest cube root? No. Okay, so what cube root should I be using? We're going to use the 5 cube roots with the smallest magnitude. So the smallest absolute value. What are those 5 cube roots? Or those 5 perfect cubes, excuse me. Negative 8, negative 1, 0, 1, and 8. So those are the ones that are closest to 0. Right? And really the only reason we're choosing those is to get a good picture, because that's where the graph changes its inflection. It goes from curving one way to curving the other way. Happens at 0. And boy, it's a pain in the butt to graph like 27. Right? To use that as one of our perfect cubes, that's a whole heck of a lot of tick marks. I don't want any part of that life. You know what I mean, guys? And God forbid you pick 4 cubed and have 64. Like nuts to that. So let's just write down our generalization, then we'll do then we'll draw our graph after that. Because the generalization is going to basically be the same thing as square roots, except, now let's write it with the perfect cube. Except we're using perfect cubes instead of perfect squares. Which is nice. Oops. Again, worth noting, this time the middle point is our HK. But notice this is basically still the same pattern as the square roots. Just we're using the perfect cubes instead of the perfect squares. No big deal. The domain and range here is lovely. Right? We can take the cube root of anything, positive or negative, it doesn't matter. And when we take the cube root of anything, if it was negative, we get a negative number back, and if it was positive, we get a positive number back. So the domain and range are just all real numbers, man. That's pretty rad. What does that mean when we draw our graph? Got arrows at both ends. You ready to do a numeric example of doing this? Or do you need a minute? If you need a minute, just say something, man. We're not in a rush. I'm just trying not to go so slow that it's like agonizing. You ever been in that kind of class where like it's just going so slow and you're like, what?